Another trend that we can look at on the periodic table is the trend in ionization energy. So if you look at the term ionization, it is related to forming ions, and energy is related to how much energy it takes. So if we kind of put that all together, it is the amount of energy it takes to form an ion. This is specifically relating to taking away electrons. Okay, so ionization energy is defined as the amount of energy required to remove an electron from an atom or an ion. So how hard or how easy, so how much energy is it going to require to remove an electron? That can happen from a neutral atom, or it could mean that we're taking an ion that has already lost an electron and we're removing another one, or even a third one. So ionization energy is really just that. How much energy does it take to get rid of an electron? So we're going to look at the trend as we go down a group first. Now remember, as we go down a group, each row that we go down is adding an extra energy level. So if you think about what is happening there, you're adding layer upon layer upon layer, which means that the valence electron, which is the electrons that would be removed, are farther and farther and farther away from the nucleus. The nucleus, with its positive protons, are what is holding on to those valence electrons, all of the electrons really. So the farther away that the electrons get from the nucleus, the easier it is to remove them, because the nucleus actually doesn't have a very strong pull on it anymore. So that means ionization energy is decreasing as we go down a group. That means really that it's getting easier and easier and easier to remove an electron. Okay. I think of kind of like when you haven't done your laundry for a really long time and you try to scoop up all of the laundry and you're carrying it to the laundry room, right? You're having a really hard time hanging on to everything because there's so much to hold on to. And you're probably dropping socks as you go, right? It's really hard to hang on to everything. So it would be really easy for somebody to come up and just pull something off because you're not able to hold on to it very well at all. That's kind of what I think of when I think of ionization energy going down as I go down the group. That all is called electron shielding. Electron shielding really means that every time we add an energy level, that extra full layer of electrons is now interfering with the attraction between the nucleus and the valence electrons. So think of shielding, right? It's getting in the way, or it's protecting, however you want to think of it. I would compare this to using a magnet, right? A magnet attracting to the refrigerator is very much like the nucleus attracting to the valence electrons. And if there's nothing in between the magnet and the fridge, it holds on really tight. But if I put layers between the magnet and the fridge, like one piece of paper, yeah, it probably holds on pretty well. 2 pieces of paper, it still holds pretty well. But by the time I add 3 or 4 or even maybe 5 sheets of paper, the magnet just can't hang on anymore. And that's kind of what electron shielding is like. So these electrons on the outer edge are really easy to pull off when they are really far from the nucleus because of all of those electrons in between that are getting in the way and interfering. So as we move across a period, remember that we talked about the idea that the atom is getting smaller and smaller and smaller because every proton and every electron that is added pulls closer and closer and closer together. So if we consider that's what happens across a group, then it isn't too hard to realize that the trend for ionization energy as we move across a group is for ionization energy to increase. In other words, it gets harder and harder to remove the electron because the nucleus is pulling tighter and tighter and tighter. So because of an increase in nuclear attraction, it's getting more and more difficult to pull off the valence electrons. So if we move farther to the right, we will find the elements that are holding most tightly to their valence electrons, and therefore it is hardest to remove those electrons. That would mean a high ionization energy. So here's our general trend, right? As we move down the group, we see decreasing ionization energy. It's getting easier to remove those electrons. As we move across from left to right, an increase in ionization energy. Now, that means our general trend up and to the right is for ionization energy to be increasing. Now, this arrow is a little misleading. It actually is pointing at the noble gases, but in fact, it would stop at fluorine because the noble gases don't form ions. There's no way that we're going to be able to remove their valence electrons because their valence shell is full. So actually, the element that has the highest ionization energy of all elements is fluorine. It's the smallest, but it's the mightiest, is how I think of it. That means that the one that is the easiest to steal electrons from would be francium in the bottom left-hand corner. It would be the largest atom, but it would have the weakest hold on valence electrons. Oftentimes, ionization energies are reported as either a first ionization energy or a second ionization energy based on which electron is being removed. So the first ionization energy is the amount of energy that's required to remove the very first electron. Okay? The second ionization energy then is the energy required to remove the second electron. Now, every time we move an electron, it gets harder and harder to remove the next electron because once we've pulled one away, there is now more protons in the nucleus than there are electrons. And it would actually mean that the nucleus can hold more tightly to those electrons. So it gets harder every time that you remove an electron to remove another electron. So the second ionization energy is always higher than the first. That would mean that the third ionization energy would be higher than the second, and so on. Okay. We can write equations that kind of show what this is looking like. So this E just represents any element. Okay. So if we take any neutral element and we remove an electron, so after the arrow, we show that it is now a +1 ion. It has lost one electron, and then we show over here that one electron. So the ionization energy for the first ionization would be some value. It's energy, so it's going to be measured in joules or kilojoules per mole. The second ionization would be removing the next electron, which means we actually start with an ion. We start with what we ended up with as a product from the first ionization. So now this element that has a +1 charge is going to lose the next electron. So we now will end up with a +2 charge for that element and remove that next electron. So this would represent the second ionization. And the amount of energy necessary to make that happen would be greater than the first ionization. You could keep going. So every time that we show the next ionization, we would start with the product from the previous one, remove an electron, okay? So we could just keep going on that. If you take a look at this graph represents energy over here, ionization energies in kilojoules per mole, and atomic number. So this one is kind of interesting because we see spikes and then a gradual increase and then it drops down, and a gradual increase and then it drops down. If you would get out a periodic table and follow the lines, what you would begin to recognize is that it's getting harder and harder and harder as I go across a period, and then it drops down as I start the next period, and it gets harder and harder and harder as I go across that period, and then it drops down. And each ionization gets more and more difficult, so the amount of energy required to make it happen gets higher and higher and higher.